A pleasant day to you all, dear students. This is Sir Clint. In the previous lesson, one type of chemical bonding was discussed, the ionic bond. It is the transferring of electrons to another atom. For today, you will learn another type of chemical bond, which is the covalent bond. I will show to you how covalent bonds are formed and the properties of its compounds. I hope you are ready. With that being said, let's get started. The main concept why covalent bonds are distinguishable because it occurs when pairs of electrons are shared by atoms. Take a good close look how I stress out the word shared because unlike an ionic bond where electrons are transferred, electrons are shared in covalent bonds. Atoms will covalently bond with other atoms in order to gain more stability, which is gained by forming a full electron shell. By sharing their outermost valence shells, atoms can fill up their electron shell and gain stability. Just think of it that these atoms want to join forces with another atom and share an electron in order for it to be happy and finally attain its dream of becoming one of the noble gases or become part of the elite octet circle. Nonmetals will readily form covalent bonds with other nonmetals in order to obtain stability. That is why covalent bonding is commonly seen among nonmetals. Now, look at the moving picture. What do you see? We have here two hydrogen atoms that bonded together to form a hydrogen gas H2. This molecule is part of the diatomic elements. They always come in pairs naturally. We know that hydrogen atoms only have one electron on its outermost shell. What's unique with it, similar to helium, is that in order for it to be stable, it only needs two electrons. Look at the GIF. Each hydrogen atom will share each other's single electron, forming one covalent bond. In this way, both atoms share the stability of a full valence shell. Simply, it is just a give and take situation. As what I've said, the formation of hydrogen gas involves a covalent bond. Only when two atoms of the same element form a covalent bond are the shared atoms actually shared equally between the atoms. However, when atoms of different elements, for example, H and Cl to form hydrochloric acid, share electrons through covalent bonding, the electron will be drawn more toward the atom with the higher electronegativity. So what is electronegativity? Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Another good example is chlorine. Chlorine also forms a covalent bond by sharing one electron from each other. A total of two electrons are shared. Now, look closely at the picture. How many electrons does chlorine have? If we count a single chlorine atom, 1, 2, 3, 4, 5, 6, 7. It has 7 electrons. How many electrons does chlorine need for it to be stable? It only needs 1. That is why in this picture, both of the chlorine wants to share one of its electron for it to achieve the octet rule. Since sharing is involved, covalent bond is formed. So now, if we count the product, 1, 2, 3, 4, 5, 6, 7, 8, and the other Cl, 1, 2, 3, 4, 5, 6, 7, 8, both of the atoms are now stable. Now, can you look at the green dot, this right side? So this one only participates in the chemical bonding and the rest of it does not. These black dots. Okay. These are what we call lone pairs, these black dots. These are pairs of valence electrons that are not included in the covalent bonding. However, this green dot and the other blue dot on the other Cl are what we call the bond pairs. Hence, a bond pair is a pair of electrons that is shared between two atoms, and a lone pair is a pair of electrons that is not shared between two atoms. Now, let's proceed to the types of covalent bonds. We have here the little girl from the animated movie Despicable Me. She's asking, are you single? She also wants to know how covalent bonds become single, double, and triple. Single covalent bond. A single bond is when two electrons, which is one pair of electrons, are shared between two atoms. It is depicted by a single line between the two atoms. Although this form a bond of a weaker type and has a smaller density than a double bond and a triple bond. It is the most stable because it has a lower level of reactivity, meaning it is less vulnerable in losing electrons to atoms that want to steal electrons. As shown here, hydrogen atoms bond, forming a single covalent bond. Another example that we have, so we have here a Lewis dot structure of hydrogen chloride demonstrating a single bond. Hydrogen chloride has one hydrogen atom and one chlorine atom. Hydrogen has only one valence electron, whereas chlorine has 7 valence electrons. To satisfy the octet rule, each atom gives out one electron to share with each other, thus making a single bond. I hope it's clear to your end, dear student. So let's continue. Double covalent bond. A double bond is when two atoms share two pairs of electrons with each other. It is depicted by two horizontal lines between two atoms in a molecule. This type of bond is much stronger than a single bond, but less stable. This is due to its greater amount of reactivity compared to a single bond. It is depicted by two horizontal lines between two atoms in a molecule. So as you can see, we have here oxygen covalently bonding with another oxygen to form O2, also a diatomic element in nature. Oxygen here needs two electrons for it to be stable. In this example, it needs to form a double covalent bond with another oxygen atom. You can then see a double horizontal line between the oxygen atoms. Another example, we have here a Lewis dot structure of carbon dioxide demonstrating a double bond. Carbon dioxide has a total of 1 carbon atom and 2 oxygen atoms. Each oxygen atom has 6 valence electrons, whereas the carbon atom only has 4 valence electrons. To satisfy the octet rule, carbon needs 4 more valence electrons. Since each oxygen atom has 3 lone pairs of electrons, they can each share 1 pair of electrons with carbon. As a result, filling carbon's outer valence shell. Lastly, triple covalent bond. A triple covalent bond is when 3 pairs of electrons are shared between 2 atoms in a molecule. It is the least stable out of the 3 general types of covalent bonds. It is depicted by a triple line between the 2 atoms. We have here nitrogen atoms. A nitrogen atom has 5 valence electron. It shared 3 of its electron to also gain 3 electrons to another nitrogen atom. Now, look at the picture. Let us count if both atoms are now stable. 1, 2, 3, 4, 5, 6, 7, 8. And the other nitrogen atom, 1, 2, 3, 4, 5, 6, 7, 8. Since they now both have 8 electrons, they already have attained the octet rule. Another example for triple covalent bond, we have here acetylene, demonstrating a triple bond. As you can see in the picture, acetylene has a total of 2 carbon atoms and 2 hydrogen atoms. Each hydrogen atom has 1 valence electron, whereas each carbon atom has 4 valence electron. Each carbon needs 4 more electrons, right? And each carbon needs 1 more electron. Hydrogen shares its only electron with carbon to get a full valence shell. Now, carbon has 5 electrons because each carbon atom has 5 electrons. 1 single bond from hydrogen and 3 unpaired electrons. The 2 carbons can share their unpaired electrons, forming a triple bond. Now, all of the atoms are happy with their full outer valence shell. Wait a minute! Are you still here? We are not yet done, dear students. Do you still remember electronegativity? As what I said, it is the measure of the tendency of an atom to attract a bonding pair of electrons. We have here electronegativities of elements shown in the periodic table. Pauling electronegativity values was named after Linus Pauling, the original scientist to describe the phenomena of electronegativity. The degree to which a given bond is ionic or covalent is determined by calculating the difference in electronegativity between the 2 atoms involved in the bond. As an example, consider the bond that occurs between an atom of potassium and an atom of fluorine. Fluorine has 3.9 electronegativity, while potassium has 0.82 electronegativity. Therefore, the difference in electronegativity is equal to 3.9 minus 0.82, which is equal to 3.08. The diagram shows how difference in electronegativity relates to the ionic or covalent character of a chemical bond. Remember, fluorine and potassium have a difference in electronegativity of 3.08. Since the difference in electronegativity is largely great, the bond between the 2 atoms is ionic. A bond in which the electronegativity difference is less than 1.7 is considered to be mostly covalent in character. However, at this point, we need to distinguish between 2 kinds of covalent bonds. Kinds of covalent bonds. Non-polar covalent bond. A non-polar covalent bond is a covalent bond in which the bonding electrons are shared equally between the 2 atoms. In a non-polar covalent bond, the distribution of electrical charge is balanced between the 2 atoms. Look at the picture. The 2 chlorine atoms share the pair of electrons in a single covalent bond equally, and the electron density surrounding the Cl2 molecule is asymmetrical. Also note that molecules in which the electronegativity difference is very small, less than 0.4, are also considered non-polar covalent. An example would be a bond between chlorine and bromine. We have a value of 0.2 as their difference in electronegativity. Since 0.2 is less than 0.4, it is a non-polar covalent bond. Polar covalent bond. A polar covalent bond is a covalent bond in which the atom have an unequal attraction for electrons, and so for the sharing is unequal. In a polar covalent bond, sometimes simply called a polar bond, the distribution of electrons around the molecule is no longer asymmetrical. A bond in which the electronegativity difference between the atoms is between zero point 0.4 and 1.7 is called a polar covalent bond. Now, look closely at the picture. In the polar covalent bond of HF, the electron density is unevenly distributed. There is a higher density, the yellow one, near the fluorine atom, and a lower density, the blue one, near the hydrogen atom. An easy way to illustrate the uneven electron distribution in a polar covalent bond is the use of Greek letter delta. The atom with the greater electronegativity acquires a partial negative charge, while the atom with the lesser electronegativity acquires a partial positive charge. The delta symbol is used to indicate that the quantity of charge is less than 1. A cross arrow can also be used to indicate the direction of greater electron density. That is it for the kinds of covalent bond, dear students. Okay, so we will now move on and learn the properties of covalent compounds. Mainly, its properties that we will discuss is its polarity, electrical conductivity, and thermal conductivity. We start with polarity. There are many exceptions to this rule, just as there are many exceptions in salts, which are ionic compounds that don't dissolve well in water. However, many covalent compounds are polar molecules that do dissolve well in a polar solvent, such as water. Examples of covalent compounds that dissolve well in water are, sugar and ethanol. Examples of covalent compounds that don't dissolve well in water are, oil and polymerized plastics. We will now go to its electrical conductivity. When dissolved in water, covalent compounds don't conduct electricity. Ions are needed to conduct electricity in an aqueous solution. Covalent compounds dissolve into molecules rather than deassociate with ions. So they typically do not conduct electricity very well when dissolved in water. And lastly, its thermal conductivity. Most covalent compounds have relatively low melting and boiling points, while the ions in an ionic compound are strongly attracted to each other. Covalent bonds create molecules that can separate from each other when a lower amount of energy is added to them. Therefore, molecular compounds usually have low melting and boiling points. And that is it. So that ends our lesson for today. I hope you were able to understand the concept of covalent bonds. Thank you for listening. Have a great day and continue to feed your curiosity in science.